Thank you very much. It is nice to be here. I think the first question you all have is, what in the world is a not quite black hole? So let me say a few words about that first. Starting with a black hole has this no drama horizon, and you don't meet any drama until you go far inside the black hole where you meet some strong gravity. So along with this no drama horizon comes the information paradox, and even more basic questions of where and what is the black hole entropy. So a not quite black hole has no horizon. And what's happening is that the strong gravity region comes way out to just be slightly beyond where the would-be horizon would be. And the point is that distance beyond is tiny, just something like the Planck length. So that makes this thing very close to being black, and in many ways it's hard to tell apart from a normal black hole. But there is one way, which is what I'm going to talk about, and that's the business of echoes. So you've heard of echoes, right? No? Not too much? Okay, I'm going to explain what they are. So I will be talking about gravitational waves around a Kerr background eventually. So let's just start with a scalar wave equation around the Schwarzschild background. And the point is to use this tortoise coordinate, where then the wave equation just reduces to something characterized by a simple potential. And this ends up being a potential barrier, an angular momentum potential barrier situated at the light ring. And in tortoise coordinates, we can put our origin there. And the point is that you have to go off to minus infinity in tortoise coordinates to get to the horizon. Well, for a not quite black hole, the waves have a finite travel time to the origin. And they'll just hit the origin and come back out again, assuming there's a boundary condition at the origin. So that implies some kind of boundary in this picture at some finite negative tortoise coordinate, and that leads to this cavity structure. So we'll call the size of the cavity delta x. That's a tortoise coordinate distance. And more important is the round trip travel time in this cavity, which is just delta t is 2 delta x. And that simple relation is due to the fact of tortoise coordinates. In those coordinates, the speed of light is basically 1. If you had seen anything about echoes, you probably would have seen a plot like this. So the merger has occurred, and the ring down signal gets emitted towards us, and it's originating around that light ring radius. But at the same time, there's an ingoing pulse as well. And in a black hole, that's lost forever. But in our picture, that gets reflected off the origin. It comes back out to this potential barrier. Some of it gets through, some of it goes back in. And that gives you the echo structure.
So you still get echoes even if you don't have any reflecting boundary, just because some fraction of the massless field is trapped near the light ring, but it has a very different time structure.
Oh, you're referring to something else slightly different than?
Well, it's just, you notice
yeah.
some radiation field excited around the black hole. Some of it will get trapped in orbits, which take a long time
okay.
to get
Yeah.
and they take a long time
Yeah.
to get out. That can go around multiple.
Right, okay. I'm talking about something very regular. Yeah, so.
Well, but that has a clear periodicity and infinity.
Yeah.
But very different, I think very different sequence of brightnesses.
Okay. And then another question is, how did I end up with looking at LIGO data? So it's starting from a very theoretical starting point where we were considering quantum gravity as a quantum field theory in analogy with QCD. And to do that, we were adapting an old proposal of a UV completion of gravity. And this is called quadratic gravity. So we were looking at this theory and ended up studying some of the solutions and looking at these not quite black hole solutions of the type I've just described. So the lucky break number one is that Cardoso and Pani just around this time was pointing out the connection between echoes and echoes. So their ECOs are exotic compact objects. And yeah, they were pointing out this type of echo structure. So our solutions then, we realized, are very natural ECOs. And in our theory, we get some kind of rough prediction for what the time delay should be. And this prediction turned out to be somewhat different from what others were assuming. So we said, well, this is something nice that should be looked for. Lucky break number two is that LIGO was releasing public data around that time. So we said, well, we better hurry and join some other outsiders looking for echoes. And we developed our own strategy. And at that time, yeah, I thought we had to hurry before LIGO just took over the whole field. But that didn't happen. LIGO did not take over the echo search themselves, and they still haven't. So it's given people like us a lot of time to very gradually figure out what we're doing. And who knows whether I actually am. But anyway, so most recently I've been able to obtain p-values for these apparent signals I'm seeing in all 10 black hole merger events. Instead of giving a list of papers, I'll just mention my collaborators. My former postdoc, Jing Ren, was involved from the very beginning. I have one of my students involved with the echo part. But the actual search I'm talking about is actually done on my own, so I take the blame for that. And here's the list of p-values, which would well appear at the end of the talk, but I thought I should show you now. So that's where I'm leading to. So I have to explain what the signals are and how I'm getting these numbers. So I'll start with the theory, and I'm just going to give a big picture view of the theory. And it starts with this question: how does nature generate a mass scale? I think the only known way, or the only way that's known for sure to occur in nature, is the QCD way. So QCD is an asymptotically free theory. It's a UV complete theory. The running coupling does then grow strong in the IR. And that scale at which it grows strong, it defines this mass scale. It's the mass scale of strong interactions. So that mass scale sets the overall scale of the whole QCD spectrum. And then below that scale, we have a theory of pions. And at low energies, that's also a weak theory. So QCD is an example with a well-defined UV theory, which is weak, and also a well-defined IR theory, which is also weak. And there's just some range of momenta that involves the strong interactions. So our question at the start was, can the same work for the Planck mass? And that's where this theory of quadratic gravity comes in. So quadratic gravity means quadratic in the curvatures. And that also has an asymptotically free coupling. And this theory was, well, it has been known for a long time to be a renormalizable quantum field theory. So in the same way then, we can imagine that running coupling grows strong, and that growing strong defines the Planck scale.
Why is it renormalizable, whereas I understand that Einstein gravity isn't?
The higher derivatives change the UV behavior of loop diagrams. So it's actually, the propagator goes like 1 over k to the 4th. So that makes it more under control in the UV. Whereas Einstein's theory is much like that pion theory. It by itself is also non-renormalizable. So it gets embedded in a bigger theory called QCD, which is renormalizable. So here's I'll put a little more details into this picture. So in the UV, I'm considering a version of quadratic gravity that's that has classical scale invariance. And so that means there's no mass terms or explicit masses in the theory at all. And that means no Einstein term. So this is a little different from what other people will call quadratic gravity. But it's more like QCD. This is like QCD has classical scale invariance. So there are two terms, the Weyl squared term and just the R squared term. The Weyl squared term has a coupling which is asymptotically free. The Weyl squared term also plays a role in these solutions I'm going to be talking about. The R squared term describes a scalar degree of freedom, and the story there is that that degree of freedom just decouples in the far UV. Okay, so we're just making the same assumptions as for QCD, that the gauge symmetry in this case is diff invariance, is not broken by the strong interactions, like in QCD. Like in QCD, we're assuming a mass scale gets generated. So those two facts then determine what the low energy theory is. It's determined by the symmetries and the fact that there can be a mass, which is the Planck mass. And that leads to the Einstein term appearing in the effective theory. And at low energies, that dominates, even though there's a whole series of higher derivative terms as well. Okay, so now this leads to this possibility that all black holes are replaced by not quite black holes. And I'm saying that that's only possible because we have a UV complete theory. So this UV complete theory allows for this different endpoint of gravitational collapse. So I showed at the very beginning that not quite black holes have a low curvature exterior region, which is described by Einstein's theory, and a high curvature interior region dominated by the quadratic terms. So it's the interior structure which probes the UV completion. And if you don't have a UV completion, you can't talk about any of this. So we studied these solutions by replacing the quantum theory by a classical approximation. And so this classical action then has both the quadratic in curvature terms and the Einstein term. And we choose that because this theory has the same high and low curvature limits as the quantum theory does. So we're hoping that that gives you a pretty good approximation to these solutions.
About the not quite black holes, for example, how would they, what's the maximum spin and maximum charge they can hold?
Well, the only solutions we have right now are the static ones. So we haven't got solutions that have spin, and we haven't put charge in. As you're probably thinking, well, the real things out there do have spins. So I'm going to explain the approximation I'm going to make to describe that situation.
Just because some black holes are close to maximum spin. So if there's a lower limit on not quite black holes, then you have there's a way to test this theory. Observation work.
Yeah, well, I'm claiming these things are extremely close to being black holes. So I expect, even in the things you're talking about, that they're going to be very similar. So getting back to what these things look like with a real actual metric, so the spherically symmetric metric with these A and B functions. So these solutions are such that near the origin, those two functions are going like R squared. And so that led to a particular name of these particular examples of not quite black holes. We're calling tutu holes. And so A and B goes to 0 like R squared, and the whole metric is going to 0 like R squared at the origin. So that 0 in the metric is actually producing a naked time-like singularity. So the curvatures do blow up. Actually, the scalar curvature doesn't, but the other curvature invariants do. But as we go on here, we're going to see that this seems to be a very benign singularity. The various integral quantities that we're going to consider are finite. For example, the action of this solution is finite. And the other thing you might worry about involves how waves behave around this background. So let's go back to our scalar wave equation. but in the original coordinates, RT coordinates. So B over A is then just the square of the speed of light in those coordinates. So the first two terms have not changed much. It's this term, which is quite different now, because B is going to 0 like r squared. So that centrifugal barrier term is now not there anymore. So that's saying that all these waves behave like L equals 0 waves or S waves near the origin. But everything else, for example, the fact that there's only one physical finite energy solution is still true here as it is in flat space. So because there's only one physical solution, that means the boundary condition implied at the origin is well determined.
Sorry, just so clear, you're saying that the interior reflecting barrier is the singularity of the origin?
Yes, it's the origin.
So this is different from the other echoes where you have some other structure at the putative horizon and that's something different.
Yeah, you're talking about something more like a truncated black hole. I'll show the comparison, yeah. Okay, so the wave equation, because of this, doesn't face any ambiguity or ill-defined time evolution. So I'm calling the wave equation in that case non-singular. So yeah, because all of quantum field theory then is based on the wave equation, you might tend to think that this background will allow a well-defined quantum field theory. Okay, so these 2-2 holes come in two types: the small ones given by the Planck size, and then these large ones of any size. And they don't have any upper limit on their size, so like black holes. And the inner structure of these two types are quite different. For the large ones, two different ones of different sizes have interiors that are just related by a simple scaling. So once you have one solution, you have that solution for all. Now this is not unlike the situation in QCD. We know of hadrons with a fixed size, but QCD also has these possible quark matter states. And they're variable in size. It can extend all the way up to neutron stars. And in fact, there's still discussion of whether neutron stars can be quark matter stars. So I'm just bringing this up as another example of how a theory that's defined by one particular mass scale can have these solutions that are arbitrarily large. And in both cases, in some sense, it's involving strong interactions of the theory. So in the QCD case, what's going on is the chiral condensate is getting suppressed in the interior, whereas in the gravity case, it's the volume element, as we'll see. Okay, so I've mentioned that the Weyl square term in the action is the essential term for these solutions. And we were looking at these using a thin shell as a matter source. That's what we did with Jing. Then I found these solutions that are sourced by just an ordinary relativistic gas. So just rho equals 3 times the pressure. And the local temperature is from hydrostatic equilibrium is just related to this temperature at infinity if the whole thing is in equilibrium, divided by the square root of this B function.
But isn't the B function going to zero?
Yes, so this temperature also is singular at the origin. But as I'm going to just say, the entropy is related to this hot gas. A hot gas has entropy. And we can calculate the entropy, and that's another example of an integral which is finite. And it actually gives an area law for entropy. Okay, so I'll show the results in the next slide, but we're solving the field equations of this theory with a matter source. So the whole back reaction of the matter on the metric is being totally accounted for. So then we can say that the thermodynamics and the geometry are explicitly linked. And because the temperature gets arbitrarily high, you're going to excite all the species in nature. So the thermodynamics and the particle content of the universe are linked. Neither of those things are that clear for normal black holes, but things are very clear here. So the field equations are a mess, and that's why this field has been slow to develop, I think. But you just have to deal with them numerically. So these ugly field equations determine A and B, and another combination of these quantities involving T infinity, the number of species, and this constant alpha. So then we get T infinity. It turns out to be a constant times Hawking temperature. The entropy is this integral, but again, that's a finite integral. And it gives the standard area law in red times a constant. The product of those two things is the standard black hole result. And the big difference is that we have normal energy in the gas. And when you determine what the total energy is, it's also a simple result.
I'm confused. A goes as r squared.
Yeah.
T goes like 1 over r.
Yeah. No. Oh, yes. Yeah.
So how does that integral go like r squared? Or am I missing something? The area doesn't go as r squared, or
No, there's just a finite part of that integral which has that behavior.
well, the integral itself appears to go like r. That's what I'm confused by. If the integral goes like r, how is area going like?
We can go through the details later if you want.
Okay.
Yeah. So here's an example of a numerical solution for the A and B functions. And this is for a horizon radius of 80 in Planck units. So outside that radius, it's Schwarzschild. And as soon as you go inside, this whole new solution opens up. You might think there's something drastic happening right at RH, but the curvatures are not doing anything special there. Although on a log plot, you do see some structure at RH. And by the way, so B over A is related to the square of the speed of light in those coordinates. So the speed of light is actually less than 1 everywhere, and it's finite everywhere. It's actually the smallest right here. Okay, so let's go back and compare the 2-2 hole to these other possible things we could be looking at. And so this brings up this truncated black hole. So like you were saying, the truncated black hole just introduces an artificial wall just slightly outside the horizon to introduce this boundary. So that's the black line that just ends at the wall. If we had a very, very compact star so that you could see this structure here, you would also see this centrifugal barrier. So that's quite different from a 2-2 hole. So the 2-2 hole has this structure here from the interior of the 2-2 hole, which is not a big change from the truncated black hole. And most of this range is coming from just slightly outside RH, where I just said the speed of light is getting very small. So in tortoise coordinate, it blows up that region.
So the echo time compared to truncated black hole is greater. So the crossing time is longer in the R scenario.
In our scenario, we will more or less determine what this distance is. Truncated black hole, it can be anything. But the travel time you're talking about is just how big is that cavity. And I'll give you a formula for that later. But it does involve a log of mass expresses the length over the Planck length. So because there's a large log, this distance is large. And in fact, this distance is 80 on this plot. But the more realistic value is more like 400. Does that help?
Sorry, you're saying that you can sort of just choose the distance in the truncated black hole case, but essentially you're set at an upper limit of the distance between the potential barrier and however close you want to get to the horizon. Whereas if I understand the
Well,
two-hole it's the distance from the potential barrier to the singularity, which seems that it's always strictly larger. That's just my question.
Well, I showed you the plot for the black hole where you had to go off to minus infinity to get to the horizon. So that means the wall can be arbitrarily close and get arbitrarily far in tortoise coordinates. So of these three quantities, then a 2-2 hole is like a star in the sense that it has an origin instead of some artificial wall. But from this plot, you see that the truncated black hole is actually a better approximation to the 2-2 hole. And that's going to be our way to approximate a rotating, not quite black hole. We're just going to use the Kerr metric, truncated. Okay, so you'll see a lot of ratios like this involving either delta x over m or delta t over m. And remember, m is treated like a distance here. Okay, so we're focusing on this cavity structure. That's the main picture here. And so we've seen that this effective radial description of the wave equation is of low frequency waves, or in the case of low frequency waves, is that of a 1D cavity. So one end is a wall, and the other end is this barrier that slightly leaks. And that's what leads to this echo structure. So that's this picture of Cardoso and Pani. But what if the perturbed state of the newly formed not quite black hole is more complicated? So they're assuming that there's just a simple pulse that moves back and forth. But after smashing two black holes together, is that what you're actually going to get? Just that simple perturbation? I'm not sure. So if it is more complicated, then you might not even get a simple echo structure. But that's okay, because the 1D cavity is still going to form, and it has a more general feature. And that is an evenly spaced resonance spectrum. And the spacing between these resonances is delta f, and that's just 1 over 2 delta x, or in other words, 1 over delta t. So we're relating the spacing in frequencies to the time delay, delta t. Yeah.
Are these going to be different in the quasi-normal modes of the black hole after the two black holes?
The quasi-normal modes you're talking about are giving rise to the ring down. And that's going to be the same. These echoes come out a time delay afterwards. And they're probing the cavity structure, which is completely different from a black hole. So, but you can call these the new quasi-normal modes, but they're just completely different from the black hole ones. Yeah. So that's what I'm suggesting LIGO should be thinking of as a resonance search. Where I'm from in particle physics, that's how discoveries are made, by looking for resonances. But this way of thinking doesn't seem to be true for LIGO. Okay, so just going back to the very simplest case of one pulse, so we've been working out how to calculate the waveforms. And the first 5 echoes are actually a mess, even in the simplest case. So trying to use some kind of match filter technique to pull out that signal is not going to be easy. I have said that LIGO hasn't really done an echo search. Well, that's not true. Here's one. But they're trying to use their same method that they use for the spiral inform, sorry, the in spiral of the waveform for the merger. So they're trying to model these waveforms by, in this case, generalized sine Gaussians. So that's what a generalized sine Gaussian looks like. It has 9 parameters to explain this. And then that's certainly not going to match what I just showed you. So then they would have to think of a superposition. So then they would be dealing with 9n parameters. That's a large number, and the sensitivity finding something then goes down like 1 over the square root of that large number. So I really don't think this is the way to go. Okay, on these plots, I'm choosing a greater number of echoes, 50, 150, 300. And just look at the ones on the left. So the red is the echo waveform. And there's so many echoes here that you can see them here, but they're being bunched up. Eventually, they start to merge, so you don't even have separated echoes after a while. So I've just added some green Gaussian noise on top, where it's sort of the same order at the beginning, but then you see the echo waveform gradually getting smaller, and you say, well, this looks hopeless. The longer you go, the smaller the echo waveform is. But if you take the Fourier transform and then the absolute value of the signal plus the noise, around 150 echoes, you do see some structure peeking up. And those are the evenly spaced sharp resonances that I'm talking about. And they're so closely together because of how big that time delay is. That large number of delta t over m is large, meaning that the delta f is very small. Okay, well, in the real data, we don't see anything like this. You can't just see these effects by looking at the Fourier transform. So if echoes are there, they're smaller than this, and we have to do a better job to try to extract them. Okay, so now we have to deal with the real problem, which is using our approximation of a truncated Kerr background and trying to figure out what does the spectrum actually look like. So it's a complex amplitude involving the two polarizations. And if we focus on the simplest, or the dominant angular mode, which is L equal M equal 2, then we can just look at a complex function of time. So that's the waveform we're after. It's directly related to the strain that they actually see in their detector. So how do we get that? Well, it's related to another quantity in frequency space, and this is the quantity that can be derived from something like a Tucholsky equation. Except we use this Sasaki-Nakamura equation, which is nicer than the Tucholsky equation because the effective range of those potentials is finite range. Okay, so this is these are non-trivial functions, so this is another ugly equation, but we can extract what we want from it. And here's an example of the absolute value of psi omega from that equation in the simplest case of a single pulse in the cavity. So it has this 3-bump structure. There's a 0 here that's actually what we call the special frequency. It's related to the spin. It's the spin of the Kerr black hole. So I think you can see why then the echoes have this irregular shape, because they're coming from a 3-bump structure like that.
So can you connect this structure and the spectrum to something physical at the reflecting barrier at the origin while it's selecting out? That's my question.
Well, I don't think it's easy to see. Well, the fact that I mean, we know the spacing, right? So we know there's going to be many of these spikes. The overall modulation of those spikes just has to be gotten from solving the equation.
Yeah, I guess I'm a little confused because it's not immediately clear to me with how you put your boundary condition at the origin, your reflecting barrier, why that would select that, why that would result in some structure in the spectrum.
Well, it's if it wasn't spinning, then you wouldn't have that 0 for one thing, right? So that's a complication of the Kerr case. And actually, I think in the short shell case, you just have those two symmetrical bumps. So a lot of the complication is coming from Kerr.
So what's the spacing between the adjacent peaks here?
It's what I've been calling delta F. So delta F is 1 over delta T. And delta T is this large number compared to M, or the horizon distance. So yeah, we have the size of this Kerr black hole, but there's another length scale in the problem which is much bigger. And that's the length, that's the size of this cavity in tortoise coordinates. So,
And how does this scale mass?
well, it's proportional to mass, but it has a log of the mass over the Planck length. So it's a large log that's giving you this large size and the small delta F. I'll show you that formula later. But yeah, there's a definite formula that people have already gotten from this truncated Kerr situation. Okay, so I mentioned that how do we know that that's as simple as that the initial condition is just one simple pulse. So we can model a much more complicated situation. We can put in 100 of these random pulses moving in different directions, and starting at different places. So what happens for the resonance spectrum, it just gets modulated in some crazy way, but it's still there. Whereas the echo waveform is gone. I mean, you just get garbage. So this is a strong indication that the resonance spectrum is very robust and the echoes are not. So. Well, there's one more step we have to do to make contact with what LIGO actually measures. Because I've been talking about a complex waveform, but when LIGO gives data, it's just a set of real numbers. So effectively, they've done a projection of that, the two polarizations into just one set of numbers, which depends on how the detector is oriented with respect to the source. So we have to model that projection as well, and all we're going to do is take the real part of our complex waveform. Okay, so then we can think of looking for this resonance pattern. We choose some time duration of the data, which is given by the number of echoes in that range times the time delay. Take the fast Fourier transform, then take the absolute value. And if we start with this real projection, then what we end up with is something not like I was showing you for psi omega. It's going to be something else in frequency space. And that's the thing that we can actually look for in the data. So I'm calling this h of f. So here's an example of a spectrum like this. NE is large, 180. The spin is 2/3. The mass is 50 solar masses. And here's this large number again. And I'm eventually going to show you a formula with a log in it that tells you why that's so large. So now we're just looking at positive frequencies, because that real projection. But I think you can see here that there's a low frequency structure superimposed on the rest of this. And that low frequency structure is actually coming from what was originally the negative frequency structure in the psi omega. So that's giving us a kind of a two-component structure in the thing we actually will be looking for. So I mentioned that all other echo searches try to model the full waveform. And in frequency space, you'd have to include the phase information if you wanted to do that. And here's what it looks like, the phase of h of f. It's a mess. So again, I don't think we should be trying to use some match filter technique that would have to model all that stuff. And the resonant search just needs the absolute value of H. Okay, I'm just going to continue with the story of how we're looking for these resonances. So I've got some set of data in frequency space. I will then bandpass it to lie within some min and max frequencies. And to pick out these spikes, we're going to just comb the data with a comb. So this is a comb in frequency space. It's got a shift, an overall shift, and a spacing. So those two things have to be adjusted and see whether they can match up to what's actually in the data. I've just shown 5 teeth of the comb, but of course, as you see, we need more like maybe 80 of these teeth to pick up what's actually in the data. So the goal then is to do that for the 2 detectors, some amplitude that you get by multiplying this comb onto the data, and see if there's a correlated enhancement of those 2 amplitudes for some particular spacing and shift. So here are the details. I don't think I'll go through the details, but it's explicitly given here. So anyone wanting to reproduce what I'm doing can easily do it. So at this stage, I'm doing a maximum over something related to the shift. So that's been taken care of, and C then is still a function of the spacing. So in a signal plot then, I'm going to be plotting this correlation as a function of the spacing. So I call that a signal plot, and these are the kind of plots that I use to look for a signal. So yeah, it's correlation versus spacing, which is delta F. And then I just take a discrete set of those possible spacings given by integer n defined in this way. Okay, so while I look for a peak, I can arrange it to sit right at a particular value here, which is just the number of echoes. So t is still free to adjust, so I can adjust t to always fit in a certain number of echoes. And at the same time, I can tune delta t to try to get a peak. Now, what's happening when you do see a peak, it makes sense that if you tune delta t, that you can enhance the size of the peak, right? Because we've got a comb with many teeth, and you're trying to make that match up with the data with many spikes. So you're going to have to choose the spacing of the teeth very finely to get this spike in the correlation. So that's all to be expected, and that's the type of thing we see. I mentioned the bandpass, and it's one of these things that I also use to optimize the signal. So I vary the number of echoes, just a multiple of 10, and I also use the data to tell me what bandpass maximizes the signal. But that's good because the bandpass can be compared directly to the spectrum. The spectrum is predicted by these other quantities that are being measured. So it's a data-driven bandpass that can be compared to the theoretical spectrum. So here's an example of such a plot. So the spectrum you've seen, the bandpass is in yellow. I've also put on the noise spectra, the so-called amplitude spectral densities, which are used to whiten the data to begin with. Okay, so the normalization of those two curves does mean something, whereas the normalization of the spectrum doesn't mean anything. It just fills up the plot. So that's why I say it's just proportional to something.
Over your bandpass, are you weighting by the LIGO sensitivity occurs? Because the sensitivity varied as a function of the frequency. And so
Well,
you can check consistency based off of the frequencies.
no, I've just, as explained on the previous, so in this region, like you're saying, it's pretty flat. So your effect is not very big here. But I'm just doing something quite simple, just, yeah, just what I said. Just apply a comb to the raw data after you whiten the data. So back on the signal plot, you see all these wiggles, which are the noise. It would be nice to know the distribution of these wiggles to get a better sense of how strong the signal is. And so that's what I'm doing here. We can generate many background versions of the signal plot by just using ranges of data outside the signal region. And while we do that, we can check that they don't display any excess correlation right at the signal point. And that turns out to be true in all cases except one exception, which you can ask me about later. Okay, so we've got many versions, background versions of the signal plot. So we got lots of correlation values for background, then we can fit them all to a PDF. And I'm choosing something called a generalized gamma of this form. So it has these parameters, alpha, beta, scale parameter, location parameter. Do a maximum likelihood fit to something like 20,000 values, and you get this red curve. And then I put on top of that just a histogram to show how well it's doing. So now we can compare the background distribution to where the signal is located. So I'm going to go through 10 events now, showing these two plots, the spectrum plot and the background PDF plot. One last thing is that the 10 events can be grouped into 3 categories depending on which of these 3 spins most closely matches what LIGO says it is. There are other details on this slide I won't get into. Okay, so here's the first event, and you've already seen those 2 plots. So I'm going to be giving NE in each case, the delta F, which you can see is determined quite accurately. And for each case, I'll give delta T over M, and you can see how that changes from one event to the next. And the spin I've just said. So this first one is a fairly strong signal. And the second one is the weakest signal. So the signal is not even out on the tail. Now here's a smaller mass event. So smaller mass means smaller cavity and therefore larger frequency spacings. So it's ranging over a much broader range of frequencies. And now what you're talking about might have some influence because it's going up here. Okay, so again, the bandpass is just determined by the optimization of the signal. This is another small mass event. And see delta T over M is still around 800 or 900.
So something I don't understand. Shouldn't you fit all the parameters at once? So it seems like you fit individual parameters for different black holes, but it seems like there should be a single parameter that you fit for all of those. If it's the same mechanism.
So which quantity are you talking about? Like delta F, for example, is directly inversely proportional to m. So you can't fit one delta f.
So maybe you say this again, because what you told earlier is that you look at a single case and then you tune the delta f and you tune parameters for each black hole individually. And it seems to me like there should be a single parameter that fits all black holes at the same time, right? Because they all scale with the mass in the same way. So can you explain again how you do a fit for an individual event?
I tune delta t.
Okay.
And even though I have some rough idea where to look because I know what the mass is, so, but that doesn't tell me it to any great accuracy, so I have to search to find that spike in the signal plot. And then to further optimize, I choose an NE.
I see. So you have two, so it means that you have two, for each event you have two free parameters.
And then the bandpass. So, but as you see, the bandpass is something I'm comparing to theory. So it's not just some arbitrary parameter that's free to choose. It's something that's determined that then I check with the spectrum.
My point is, why would you tune these parameters individually for between different events? Right? Shouldn't it just scale with the mass?
Well, the spectrum scales with various quantities.
Right, no, but the delta t and NE that you use, why would it be individual? Why would it be unique for two events?
Well, if we knew the mass that LIGO measures to this accuracy, then yeah, you could maybe make a prediction. But m is not known very well at all.
We only need the trip mass instead of final mass. That's what we'll
Right. Yes.
Would be something good to discover with cookies, so we put that on side.
So I just want to get to this 729 event, which is the most striking. What happens here is that two bandpasses give me signals. And so two plots like this. In both cases, the signal is strong. So the two bandpasses are kind of lining up with that two-component structure, which shows up to a greater extent in this case of a larger spin. So this 729 has that 0.81 spin. So it's quite a bit larger than all the others. And it's kind of separated these two components. And if I actually try to use just one bandpass over the whole thing, then the signal goes away. So it's saying that those two components are actually somewhat shifted with respect to each other. So a common comb doesn't match. And the other thing is that these are two different bandpasses, so two completely different frequency ranges, and yet delta F is coming out basically identical for those two bandpasses. Okay, so those are the 10 events. Here's the neutron star event, which I don't include in what I'm telling you next because LIGO doesn't even actually tell you what the mass and the spin are in that case. So I just chosen some values. Okay, so here finally, so I'm almost finished. This is the formula I've kept alluding to for delta T over M for a truncated Kerr black hole. It has this large log. So that log is of order of 100. And with these other factors, get you up to 800. So that's what we're going to do. Everything in this formula now is determined. LIGO determines these three quantities, and I'm determining delta T. So then we can determine this eta. So what is eta? Well, eta determines what I mentioned at the very beginning, that distance from the would-be horizon to where you get out to the Schwarzschild form of this metric. So that's a tiny distance. which is related to either the Planck mass or what you call the proper Planck mass. And the proper Planck mass, because this A function is so large, the proper Planck mass is actually even much smaller than the ordinary Planck mass, or the so-called coordinate Planck mass. But, okay, so here's the plot. I put all these values of eta determined in the way I just said, and they line up pretty well, even better than you might think.
Each one of these is how many sigma?
Well, first of all, the errors here are all LIGO errors. They're nothing to do with my errors. And this plot doesn't say anything about the strength of the signals. And I've combined the LIGO errors as if they were all non-correlated, which is probably not true. So my error bars here are probably larger than what LIGO would say. But anyway, if I use those error bars, then this is the 1 sigma band, and this is the result for eta. So either it's a very small number times the ordinary Planck length, or it's a large number times the proper Planck length. Just to show the effect of the spin and the redshift factors in that formula, I can just enlarge the y-axis, and then in this plot, take off those 2 factors in that formula. So what happens is that eta becomes greater than 2 everywhere, which is not physically making much sense, because then it's delta r is much smaller than the proper Planck length. And the other thing is this 729 goes way up. So the fact that those factors are bringing it into line with the others is an indication that we're seeing some dramatic effect of the mass and spin and the redshift. And, okay, so I just wanted to end. Okay, I should stop. I just said, okay, here's the slide if you want to look at it. Tells you where I got those p-values from. It's basically the area of this curve here times some number of values that I'm allowing to look for the delta t. In this case, that's 28. So I take that area, multiply by 28, and that's a p-value. Are there experts on p-values here?
Enough to know that it's not used as a standard anymore.
And even knowing how to combine them is not a well-defined procedure. But there are some popular methods, and when you try them out here, you get these extremely small combined p-values.
It's still used for drug trials. It's still used for drug trials.
I think
Let's move on.
These events, some have much higher signal to noise than the other. But the first one, I think, was naked eye, the power spectrum. And so I thought that...
Sorry, which one was naked eye? There's no naked eye here.
No, I'm saying, just take the plain vanilla binary black hole template. I mean, the first LIGO event was...
Oh, yeah.
Okay.
Yes.
And so if you're talking about an echo of comparable magnitude to the initial pulse.
No, I showed you that example where I put down that green noise.
Yeah.
And in that case, the spikes were larger than anything I'm seeing in the real data. So that was an example of echoes much larger than what's true.
Let's say for the first event,
Yeah.
which was, I think, the highest signal, was someone who's correct me if data on that. What are we talking about in terms of the magnitude of the echo, of the first echo relative to the initial
The ring down. So we're comparing it to the ring down, not the peak value.
Fine, but
Yeah, so what's the scaling relation between big A on little h for the main inspiro signature and the echo signature?
Well, if you can think more of the ring down, which is hard to pick out from any data, right? These results are suggesting that the first pulse, or sorry, the first echo is still somewhat smaller than that ring down. Because in that case where it was comparable, then the spikes were seen by the naked eye, which is not true. So if you bring those spikes down, that's how much lower the first echo is than the ring down.
So my question is, are the relative strengths of the amplitude of the echoes you're seeing, do they map with the SNR of the mean signal in the detector?
In my method, I don't pick out any amplitude. So,
It would be hard to test the relative, right? It seems, are we wrong that the amplitude should scale, the amplitude of the echo should scale with the amplitude of the signal?
it's not clear. For example, the highest signal event was the highest mass and highest spin. So mass and spin may have a bigger effect than anything else.
Have you interacted directly with LIGO people on this?
Early on I have, and
I get the feeling that it would be a useful exercise from both directions, just, you know, to really go over the nuts and bolts of how you do the analysis and so on.
when I talk to them, I can't get over the hump that they're doing their match filter, and I'm not. As soon as I say I'm not doing your match filter, they say, well, I don't know what you're doing. So. He was here when I was just starting this, and so we didn't talk too much, no.
He, you know, as a training, is very much formal, well-versed, and he's quite flexible in his thinking. He's not only a data, I don't mean that pejoratively. Only a data analysis.
Right, yeah. I agree, eventually we have to wait for LIGO to tell us something about any of this. So, but hopefully as these type of results come out, they get somewhat interested and maybe think for themselves how the best way to look is. But so far it hasn't happened.
You want to wrap up?
Thanks.
Yeah.
Is it the conclusion slide?
Pardon?
Is it the conclusion slide? Or?
Well, everything I've said already, so it's okay.
So, you have a question?
I'm just curious, suppose that you take
Okay, thank you.
without echoes, so just regular ring, classical ring down. You add on top of this the noise from LIGO, and you carry out your analysis. Will you get, what kind of signal will you get? I'm just curious how sensitive you are to this effect that you were describing, not classical GR effect.
So here's the first echo, and it's of order the noise. And that's not to be expected. You'd expect the first echo to be, I don't know, some factors smaller than the ring down. But in this case, it gave a signal that was too big because we don't see something like that showing up. So I'm saying that the actual signal might be down around here, not really much smaller, but something that's just below where you can see it.
Thank you.
Okay.